Hi there everyone, welcome back. We are working on our next lesson in thermodynamics, and today is kind of a big one because today we're going to really look at some of the thermodynamic processes that kind of make this unit special. So we're going to start off here by just defining our first law of thermodynamics. Now, you already know this one, but you just know it by a different name. The first law of thermodynamics is essentially just conservation of energy. So that's nothing new for you. Energy cannot be created or destroyed, yada, yada, yada. But we're going to think about this, and the conservation of energy takes many different forms. You probably used it mostly with mechanical energy, a roller coaster going down the hill, potential turning into kinetic, and so on. But we're going to talk about it in terms of how it affects ideal gases. So when we write the conservation of energy, in that sense, we write it a little bit differently, although it really ultimately means the same thing. We say this, we say delta U is equal to Q plus W. Now, some of those terms are going to be new for us. So let's see if we can define a few of them. The first one is U. So for an ideal gas, U is what we call the internal energy. So this is a change in internal energy. And so you can imagine if you have a gas, maybe like in a canister, that those particles have energy because they're bouncing around and because they're particles. And you can change that energy. And one way that you can change that energy is you could cause heat to flow into them. So that's our value for Q there. Q is heat. And a reminder that heat is really just the flow of thermal energy. So you could picture taking a canister of gas, and I wouldn't recommend this, but you could imagine putting it on a fire, and so heat flows into the gas, and there you go. But the other way that you could change the internal energy of the gas would be to do work on the gas, and that's that W term there, so work. And we are going to define work as being done on the gas. You could imagine if you've got a canister of gas and you were to compress it all of a sudden, that would change the energy of the particles inside that gas as well. Now, one thing that sometimes gets a little bit confusing is our definitions, because we've thrown around a bunch of different terms for energy. Like we talked about thermal energy, we talked about kinetic energy, and we're talking about internal energy and all these things. And the thing to realize is that because we're talking about ideal gases, it's going to be a little bit simpler than it all sounds. So technically speaking, strictly speaking, the internal energy of a gas is actually a combination of all of the kinetic energy due to the particles moving. So obviously the particles are whipping around. They've got kinetic energy, but also particles tend to exert forces on one another. They're sticky. They attach to each other. There's van der Waals forces and London forces and all those wonderful things you learn about in chemistry. And so there's going to be potential energy due to those interactions. So the potential energy due to particle interactions. Now, the thing to recognize, though, is that we are talking about ideal gases, and this is where our lives get much more simpler. One of the assumptions we make about an ideal gas is there are no particle interactions. So we don't have to worry about that internal energy part. That essentially means that for our purposes, the internal energy is just going to be equal to the energy due to the particles moving around, due to their kinetic energy, which we have already defined as being the thermal energy. So a little bit simpler for us. Now, when you go on in the world of thermodynamics, we might not make those simplified assumptions, but for now, that's what we're going to do. Okay, so we've got our internal energy, which is just equal to the thermal energy of the gas particles, and we can add or take away heat to change their energy, or we can do work or get it to do work for us. And so, in terms of the work done on a gas, we're going to define work done on a gas as negative P delta V. Okay, so you can see here that if I've got a gas and I were to compress it or expand it, then in either one of those cases, work is being done because the volume is changing. And that's a key point, that in order for work to be done on a gas, there has to be some change in volume. So the first thing to recognize that, and this is just going to depend, different textbooks define this differently. So what we are going to do is we are going to define work as being work done on the gas. Sometimes we want to define it as work being done by the gas, but we are going to default and say that the work is the work done on the gas. And that explains why that negative sign is there, okay? Because you could imagine that if I have a gas in a canister and a piston or something, and that gas expands, then work is being done by the gas. The gas expands and maybe it lifts the piston. And so in that case, the work would be negative. You can see that from the equation I just gave you, because if the change in volume is positive, and the pressure, of course, will be positive, that negative sign out front makes the whole thing negative. And conversely, if I take a gas and I compress it, well, then my change in volume is negative, my pressure is positive, but then that negative sign out front cancels out the negative sign from the change in volume. And so if I compress a gas, the work is positive. Okay, awesome. So, we're going to get now to the heavy lifting. So one of the things we talk about in thermodynamics all the time is there's a number of what we call thermodynamic processes, which is basically stuff that we can do to ideal gases and see how they behave. Okay, so there's 4 of these processes. And I can't stress this enough. These are all ideal gases in idealized processes. So these 4 things rarely ever happen, or if ever, perfectly happen in the real world, but sometimes they're good approximations. So that's why we kind of need to know what they are. So the first one is isobaric, and we're going to see this iso a lot. Iso, if you don't know, means the same, right? So like an isosceles triangle has 2 sides that are the same. I think that's how it's pronounced. Then an isobaric process is one where the pressure stays constant. Pressure is constant. Now, I think it's useful to think about, there's 3 things I want to do. I'm going to do that for each of these processes. And so one, we're going to graph it. We're going to look at a pressure versus volume graph and think about, okay, what will that look like on a pressure volume graph? And then the second thing I want to do is I want to think about like these 2 equations we looked at. So my work equation and my first law of thermodynamics. I want to kind of think about what happens to those equations in these types of processes. And the last one we're going to look at is maybe just a real world example or just something that we can visualize of what this might actually look like. So first things first, an isobaric process where let's say we're going to stay at a constant pressure, but our volume is going to change. So you can imagine something like this, where I start at a point on this graph, okay, and if I keep my pressure constant and I move to another point on this diagram, that was an isobaric process. So maybe I move from A to B. And you can see that if I go from A to B, going this way, this would be an expansion, right? So that way I'm expanding. So you could say that that is an isobaric expansion. Maybe I've got, again, a gas that's just, well, it's just expanding. It's taking up more volume. So let's think about our 2 equations that we learned above there. The first is the work one. Let's look at that. So work is going to equal negative P delta V. Okay, so let's look at this. Well, I started at A and I moved to B. What I want you to realize is if I take a look at this graph here, okay, and if I were to find the area under this graph, let's think about what that would be. So this side of the rectangle will be the pressure, and of course that stays the same. This side right here represents my change in volume because I started at one volume and I moved to the other. So you can see right here that the work done really is just the area under the graph because it's pressure times a change in volume. What you will need to do is you will need to think, okay, well, is the work going to be positive or negative? And that's going to depend on which way we go. If I go from A to B, that's an expansion and the work would be negative. But of course, if I were to go the other way, if I was to go from B back to A, that would be a compression. And then I am doing work on the gas. And so the work in that case would be positive. So I'm going to leave it up to you to figure out whether the sign should be positive or negative. But the amount of work done, you can see, is just going to be the area under the graph. And of course, if you had the values, you could just plug them into the equation. It would give you the same answer. So then the second thing to think about is our first law of thermodynamics, which is our change of internal energy is equal to Q plus W. Now, maybe this was a bad one to start with, but in this case, there's no simplification that we can make here. In this process, as I go from A to B, then heat is going to flow and work is being done. So the total change in internal energy, I would need to know a little bit about both those things to find the change in internal energy of the gas. Now, let's think about this as an example. So what would it look like? What would be something I could do where I keep the pressure constant, but I change the volume? So one way to visualize this would be like, imagine I've got like a balloon, okay, and the balloon's just full of air, and nothing special about that, but it's like a really, really hot, sunny day for some reason, and it's just the sun is just beating down on this balloon. You could imagine that, maybe not a ton, maybe not like a lot, maybe not as much as I'm going to exaggerate here, but you could imagine that the balloon is going to increase in volume as it heats up. And the pressure is the same, right? Because the air pressure pushing back on the balloon doesn't change, but the size of the balloon might grow, the volume might expand because of heat flowing in to the into the system. Okay, so that might be an example of an isobaric, or an approximately isobaric process. Okay, so the second process we're going to talk about gets two names for some reason. It's either called isochoric or isovolumetric, and of course what we mean by that is volume is constant. Okay. So we're going to kind of do the same run through about like a look at the PV diagram and so on. So let's think about what a PV diagram would look like for an isochoric or isovolumetric process. Okay, well, maybe I start on my PV diagram right here. And remember that the point on this PV diagram just represents a certain pressure and volume, which all ties back to our ideal gas law, PV equals nRT. So I'm sitting there at a certain pressure and volume, and then maybe I move to another point on the graph, something like that. So I go from A here to B there. So let's think about that. Basically, my volume is staying constant, but my pressure is increasing. Okay, so let's think about our equations. We've got the first one there was, remember that work was equal to a negative P delta V. Well, the first thing to recognize is that if it's an isovolumetric process, then the volume isn't changing. And if the volume isn't changing, then this thing is zero, which means the whole thing is zero. So for an isovolumetric process, no work is done. No work is done on the gas or by the gas. That just doesn't happen. And so if I look at my first law of thermodynamics, which says that my change in internal energy is going to equal to heat plus work, well, if no work is done, then any change in the internal energy of the gas is entirely due to heat. So heat could still flow in or out, but that is only going to change the pressure of the system. It's not going to do any work. It's not going to change the volume. So what would this look like? What would be a situation like this? Well, I've got again, I do not recommend this at home, but imagine that you've got a can of beans, okay? So you've got a can of beans, and for some reason you accidentally throw it into a campfire. And you might be saying, I don't think a can of beans is an ideal gas. And to you I say, good point. But let's just suppose. So you could imagine that this container is fixed. This container is not going to change its volume, hopefully. But as heat flows into it, it is very much changing its pressure. Okay, so work isn't being done on the contents of the container because the volume isn't changing, but heat is flowing in, and the internal energy of the contents of the container are very much changing as a process. Okay. All right, so those two I think are fairly straightforward, to be honest with you. I think the next two are kind of the stranger ones, and they take a little bit of getting used to for sure. Isothermal, this is probably not a huge surprise to anyone, that isothermal is where temperature is constant. Okay, now again, and all of these processes do involve ideal gases, which, don't forget, is PV equals nRT. Okay, so just keep the ideal gas law in the back of your mind as we're imagining these things. Now, if I have a pressure volume diagram, if my pressure is constant, just remember that I could rewrite this formula as P equals nRT over V. And we know that N and R are going to be constants if it's a closed system and R is a constant. But then if temperature is also constant, then this graph is just going to be one where it's an inverse relationship between P and V. Then I'm going to get an inverse function curve, which kind of looks like this. Okay, so you can imagine a situation where I go, maybe in this case, we're going to go from A here up to B there. Okay, and so you can imagine as we go along from A to B, this is an isothermal process. And so you can imagine, like, just for example, let's say maybe this is at like 100 Kelvin. Okay, so if I stay on this line, the temperature isn't changing. We sometimes call these lines isotherms. So an isotherm is just it's a line on a PV diagram where the temperature isn't changing. So it's isothermal. Now, these are kind of hard to recognize, right? Because it's just like a curve, but like, is it isothermal? I don't know. The thing to keep in mind is what would happen if we had another isotherm on this graph, right? So like if for example, I had like this isotherm is at 100 Kelvin, what would it look like if I had an isothermal process that was at, I don't know, 500 Kelvin? Like, what would that look like on this graph? Well, the right term, it's not correct to call it parallel, but that's kind of how my brain wants to see it. These two isotherms kind of run like along each other. And of course, they can never meet because they are at a constant temperature. So maybe this one's at 500 Kelvin. So they are all anywhere on that blue line is 500 Kelvin, anywhere on the black line is 100 Kelvin. And so of course those two graphs can't meet. They kind of run along together. So what would this look like in terms of our equations? Well, if I want to find the work, I know that the work is equal to negative P delta V. And you can see from the graph here, like I'm not going to be able to find the pressure is changing, right? As opposed to when I look at that isobaric graph. So the pressure is changing and the volume is changing. So this gets pretty complicated. And the short answer to finding work for an isothermal process is you have to use calculus. And so really it is just the area under the graph. There's no easy way to find the work done other than being told or again using calculus to find it. Okay, now let's think about our first law of thermodynamics. So we know that the change in internal energy is going to equal the heat that flows in plus the work that is done. Now, let's think about this though. Because it's an ideal gas, we know that the internal energy, we're assuming that the internal energy is basically just the same thing as the thermal energy, which is the kinetic energy of the particles moving. And you'll remember in the last lesson, we learned that the kinetic energy of the particles are just proportional to the temperature. So as temperature goes up, kinetic energy goes up. So what this means is if the temperature is constant, then the kinetic energy of the particles is not changing. And if the kinetic energy doesn't change, then the internal energy doesn't change, which means this whole thing equals 0. And so basically what that means is we get this statement here that says Q equals negative W or W equals negative Q. So the internal energy stays the same. That just means that any work that is done on the gas must be accompanied by a heat that flows out of the gas and vice versa, right? So that the internal energy of the gas has to stay constant. Now, isothermal processes are particularly tricky to visualize, and I don't have a great way of picturing it, but I will do my best. So imagine we have a piston, okay? So imagine I've got a piston and it's filled with some ideal gas, okay? And I've got this piston I'm going to drive down on. Now, this ideal gas, these particles are moving around inside. And so now imagine I've got this piston, and the thing about it is I'm going to compress it, okay? So I'm going to compress it, but I'm going to compress it like very, very, very slowly. So I'm going to compress like this, compress very slowly. Now, you know that if I compress a gas, that if I just compress the gas like this, then the temperature is going to go up, obviously. But what if I did that very slowly? If I compress the gas just a little bit, then technically the temperature of the gas would increase slightly. But if the temperature of the gas is greater than its surroundings, then heat would flow out of the gas into the surroundings. And so then I could compress the gas just a little bit more, and the temperature of the gas would go up, and then it would be hotter than its surroundings, and the temperature would flow into the surroundings, and I could repeat this process forever. The thing about it is, for this to be truly isothermal, I would have to take virtually an infinitely long amount of time for the process to happen, for it to be truly isothermal. But I suppose for any situation where I go fairly slowly with my compression, any amount of increase in temperature of the gas is going to fairly rapidly end up moving into the surroundings. And so you can think about those processes, those slow compressions or expansions, as being roughly isothermal. Okay, that brings us to our last process, which is adiabatic. Now, an adiabatic process is one where no heat flows. Okay. That is not the same as saying isothermal. Isothermal, the temperature doesn't change. Adiabatic, there is no heat flow in or out of the system. The temperature can very much change, as we'll see in a second here, okay? So adiabatic processes are even trickier to visualize than isothermal ones, but the best way that I've found to do that is to actually think about two isotherms. So imagine I've got my graph and I've got two isotherms. I'm just going to kind of draw them dotted lines here. So I've got two isotherms on my graph that look like this. So these are just my isotherms. Okay, now the key to remind there, so those two isotherms are at constant, each one is at a constant temperature, right? Whatever temperature that is. Now, an adiabatic process is one where I start on one isotherm, I jump up to another isotherm. Okay, so I jump up between isotherms. So as I go from A to B here, you can see that this is an adiabatic compression because my volume has gotten smaller. During this adiabatic compression, I went from a lower temperature and I jumped up to a higher temperature, okay? And so, so that's adiabatic. Now, let's think about our two terms. So our two equations. So work equals negative P delta V. And just like with what we saw with isotherms, I can't easily calculate the work there because the pressure is changing and the volume is changing, and so therefore calculus, and so therefore the work is just the area, or maybe it's just going to be given to you when you run into a problem. But when I look at my first law, my change in internal energy is equal to Q plus W, so heat plus work. Well, for an adiabatic process, heat doesn't flow in or out, and so this heat term here is just zero, which means my change in internal energy is done only by the work. So for example, when I go from A to B, maybe I do a compression on the gas from A to B and it jumps up in temperature, that change in internal energy is entirely due to the work done on the gas, not due to heat flowing in or out. And similarly to isothermal, it's kind of hard to imagine a situation that's truly adiabatic, but let's do a comparison. So let's do the same thing with a piston. Okay, let's do that same experiment with a piston. And we're going to do a compression. So I've got my piston, okay, and I'm going to compress this gas. So what would this look like for me to have a process that is approximately adiabatic, a compression that heat, where heat doesn't have a chance to flow in or out? Well, the first thing is I could do the compression very, very quickly. So compress very fast. If I was to compress this very suddenly, then frankly the heat wouldn't have a chance to flow out of the gas, and so you could see the temperature of the gas would spike because the heat hasn't had a chance to escape. But the other thing I could do is I could insulate this whole thing. So imagine that I put this in a big chunk of insulation. Now, in this case, now the heat's going to have an even harder time escaping from the gas. So you can see that clearly in this case, when I do the compression, the temperature of the gas is going to spike right up because all of that work that I'm doing is going to change the internal energy of the gas. Okay, that is it for the first part of the thermodynamic processes video.